more simple example. In one, we will do it using PID with inherent saturation, and in another one, we build it ourselves. Alright, so let me do it this way now without this block, and I take transfer function, assuming this transfer function, I don't know, 5 over maybe 0.1 s. So assuming this is my transfer function, velocity control, a over ts plus 1, I'm controlling the speed of my motor. And look here to the scope at the output, but also I want to look at the reference. So I see both. And my reference is step. Alright, so up to now I'm doing the classical way, okay? So quickly, just doing it quickly. Of course you have open loop. So now I may tune my system quickly as I'm considering PID, normal PID. Without adding any anti-wind up or any saturation effect. Did I tune it? It's here. Okay. So this, the response that I will take. Can I take a response that saturate my? So I take parameters that saturate my controller. It depends on how much saturation is. It's anyway. So let's now keep it this way. And I will supervise as well the control signal. Okay. Here I'm looking to the control signal. Let's run. Alright. What's the system is giving me? Let's tune again. Did I want to make sure I don't have anti-wind up. Right, let's change the system now. Later on we'll figure out, but at the time being, just take simple system. I'm not sure what's going on. Later we'll figure it out. Now the goal is to show the anti-wind up in this remaining time. I did something, yeah. So please, why you don't show it to me, guys? This is, I didn't do feedback anyway. So you get the point, right? Why it happens? Because I was not doing feedback. I was doing positive feedback, not negative feedback. Okay. Anyway. So then let's tune again. Any responses is alright, I believe. Not big deal. I can have some more effort. Just okay. So I make it this way, and that's my control signal. So I want to point my control signal. I want to put a saturation at 0.5. So then, assuming my signal will saturate at 0.5 or 0.4. So then here I will be adding a saturation block. Okay. So I add a saturation block at 0. Let's keep it 0.5. Okay. So what will happen now? This is my system. You see how overshoot. Compare it to the case when I don't have this saturation. It didn't overshoot as this because it's taking the system as linear. But now, if you look here, why is the control? Yeah, here because I'm taking the control signal here. Let's take after the saturation block and look at it. You'll see like here you have a saturation F. So that's why it overshoot. Your signal here, it overshoot. So now let's implement the anti-windup method. So saturation, output saturated. When the output will be saturated, I will say it will saturate at 0.5 minus 0.5. 0.5 minus 0.5. Right? And anti-windup method, the back calculation method with KB back calculation coefficient will be calculated for us. We will tune it. Okay. So then I don't need this saturation block anymore because the saturation block it was implemented with the controller. Good. So what you do now? You tune it. You simply tune it. Okay. Let me go and tune. Click apply to apply change, then tune. Alright, let's take it this way. I can if I wish. May take the system I wish, no problem. And then, okay. So you see here, you see the saturation symbol. Then I look at it, I don't remember how much the saturation was, so we can compare. We need to, we need to remember how much the saturation was in the previous one and compare it with this one to see. But in general,
Doctor, it was 1.13.
1.3, 1.13.
Yes,
Okay, and here,
higher. Here it is high.
Okay, so the overshoot is higher. So basically,
Maybe because we took KD equal 1. It should be.
it's not tuned here. Then this is not tuned, guys.
No, it's not tuned.
I saw it should be tuned automatically with the PID, but it's not the case. So now, then what you do, you have the I parameter and your D parameter, and then you can figure out in here how to find the TR. So you have a relation between KP and TI and all of those stuff, right? You remember it from chapter part 2. We give the relation here. So like now what you do, you know the KI equal KP over TI and KD equal KPTD. So then you can find TI, which is KP over KI, and you can find TD, which is KD over KP. So if we find them, we can find TR, which is square root TI TD. So let's quickly, in the remaining 3 minutes, find them based on our value of. So I have MATLAB here, and these are the coefficient I have. Actually, I need to minimize it. I'll take it here. Okay. Yes. So now we can see better. So then TI equal KP over KI, 0.9 over 20.9. That's TI. TD equal KD KP. KD is 0.0001, so it's minus in this case 16 over KP, which is 0.9. Alright, then TR is equal to of TI times TD. So this is my TR. Then your gain, if you wish, KB equal 1 over TR. So it is 361.42. Apply this scenario. Then okay, let's me. So we reduced it a little bit, right? And saturation is less. Do you agree? You said Tariq, how much it was?
It was 1.13.
1.13. So now it is we reduce
1.015.
yeah. So this is basically how to implement anti-wind-up. You just click here, you put your saturation block as part of your actuator, and once you're done, you need to then tune it yourself. There is no automatic tuning for it. So now first you find the PID coefficient, then you tune for it. Also, if you have only PD, so you can just find a value that suits you, because you don't have derivative term for that, so you don't need TD. Any question regarding the anti-wind up? Just to clear the effect of integral in reality and how we tune it, we need to implement the anti-windup effect, which is implemented for you in MATLAB in here, or clamping method. So you can do the clamping. The clamping, if you want to do it quickly, just take 1 minute, guys. The clamping, when you say clamping, the good thing in clamping, just they implement the switch on off. So you don't need to, let's say, tune a parameter. Just you tell the integrator to go off when it is saturated. So you see it is also better than how it was before. Okay, where it is the other signal, here is the signal. So you can see, so then you don't need to calculate a coefficient version, but it's more complex in integrating it. But here, thanks to MATLAB, it's possible to do switch on off. So usually it's more smoother to have proportional rather than on-off controller. It's like kind of on-off controller. Here is kind of proportional controller you are feeling. If no questions, يعطيكم العافية. See you on next week. So let's see, resume actually. Let's take first case when we have no saturation block at all. If that's the case, so my actuator is free to go to any value, no saturation, and also my control signal can overshoot that how. If you wish, I can zoom on it, look at it, and have my cursor. Then I move my cursor from here up to here. Make sure you are not clicking on this. So click again to take it out and keeping this. So now I'm up to here. So then the value is 1. The value is 1 because it's a step. So you have to graph on this. You need to precise which selection you have. So for example, I have 1089. Let me draw them. Let me write them somewhere. Like no saturation. Maybe I draw them here. Okay. No saturation. No saturation block. First scenario. Then it has overshoot 1.089 amplitude. Well, this is not the only criteria we could compare. We could also compare the transient time and so on. But let's just keep it this way. Close it. Then take the case when I have saturation. So just I put saturation 0.5 minus 0.5. I can have it more, like maybe if you wish my actuator saturate at 0.4, 0.3. Yeah, for example. Apply, then OK. And in here I redo the simulation. So my actuator saturate. So it's capped at 0.3. And here is my output. That's my output. That's how it looks. If I zoom here, I still have some overshoot at least. And if I go to my cursor, want to know how much the maximum around here. Of course, not this point, so I need to go to the blue curve. So around 1004, very close to 1, I mean. So maybe better if I had a saturation of, so we can see it clearly. If I take saturation of 0.6, then just make, so assuming my system, so I keep some advantage for the anti-windup. So my actuator saturate at 0.6. I could zoom actually and look at it. Okay. And here is my system. So still have overshoot. My cursor moving to here. So not the yellow, is the blue. So in case of saturation, I'm introduce a saturation block, then 1.028 overshoot. So taking the saturation block, just I put a saturation on the actuator, so it will reduce the overshoot of my system, because it's a real system. So this is from here we'll do the comparison, because we have saturation in real situation. Of course, you can later on add friction, as we saw in one of our lectures, and so on. But yeah, so now let's go and see with clamping. And third, so 3 clamping, anti-wind up effect clamping, and fourth, what we call wind up back, right? That's the name we are using. Let me remember the name. Back calculation, anti-wind up back calculation method. Okay, so then what if back calculation method? How much is the overshoot? So keep the same tuning as this, the tuning we did. And here I'm allowing now what? So this is what we did was actually the back calculation. So here what you see 1028 probably was the back calculation. Let's put none. Make sure it's none, and we do our stuff. Alright, so now here we go. Makes sense. So cursor and blue and moving here. So one, okay, one, so number 2, 1128. Okay, 1128. So 1.128. So this is saturation one. It overshoot more when there is saturation, which makes sense. Yeah, it should saturate more when you are not saturating. So because you block your controller, which is the real case. In real case, so you have overshoot, which makes sense. 1128. Good. Now our result talking better. So in clamping, so now I do clamping, enable it, but with clamping method. Basically, we should back calculation clamping should work same way. If I have delay in the plant, so I can see that back calculation is better. So here, my cursor just to get some exact value for signal 2, blue one, I'm getting 1.036. 1.036 amplitude. Okay, which is fine. And then somehow same order of magnitude if I do now the backup calculation, and you remember that's the value obtained together. Then look to the system. Here you go, then it should be the value that we found at the beginning, right? Alright, it is back calculation 1.02, 1.028. Okay, so then we can have our result, so the effect of back calculation. So now, what if I have delay in my system? So let me save it for you as back calculation. And what if I have delay in my system? So this example we said we will do together next time, but I just said it's easy, so let's record it myself. You follow it, you practice it at home. So in this example, basically you have a first order system, encourage you to read them with dead time. You know what is dead time. So then the time of 2 seconds actually, and you represent the dead time in Simulink by this block function. We call it transport delay. Okay, you can name it whatever you want, but it's called in MATLAB transport delay. So if I write transport delay Simulink continuous, I should find it. Yeah, let me transport delay. MATLAB gonna close, so we'll come back. Also here it's a good illustration, illustration of the wind up defined in MATLAB in here by Paul Aquatella. So basically what he said is it may happen that the control variable reaches the actuator limits. This may happen. When this happens, the feedback loop is broken. The feedback loop is broken. Why he said that? Actually, because the system runs as an open loop, because the actuator will remain at its limit. The actuator will remain at its limit independently of the process output. So we are keeping increasing the integrator output or the PID output, but the actuator doesn't react. So it's like as an open loop. Why doesn't react? Because it saturates. So when the saturation happens, it's as if the feedback loop is broken and the system runs as an open loop. So if a controller with integrating action is used, the error, in that case, the error will continue to be integrated. Because you have error and this error will integrate. So then this is effect of having the integrator, then the negative effect of the integrator when saturation is happening. This means that the integral term may become very large. Integral term may become very large and it winds up. So we call it become range up and it winds up. This is a wind up because the integral term becomes very large. It's then required that the error has opposite sign for a long time. As a significant of this, as a consequence of this, the error will has opposite sign for a long period before things return to normal. And that's what you saw in your video last time here. So the error, it requires a long time in a negative sign before things happen and return to normal, before you start really decreasing your speed of your drone. Okay, before things return to normal, the error has opposite sign for long period. So as a conclusion, if you want, so its consequence is that any controller with integral action on it may give large transients or large overshoot when the actuator saturates. If you have saturation and you have integral action in your controller, then you need to expect a large overshoot. So you can keep it if you want, or you avoid it by implementing the anti-wind up. Good. let's do one more Simulink example together. So basically we will download this example which we have it here on MATLAB. So this is we have dead time. In addition to the first order process that we have adding dead time to the system. As I told you previously, the dead time is like it takes time to have a response after injecting the input. So if injecting the input at time t equals 0, maybe after 5 seconds, you get start to react to your input. So your process starts to react to your input 5-second lag. So this dead time causes sometimes instability of the system as well, and overshoot and a lot of problems sometimes. So this is we're adding that time, keeping in mind that the anti-windup method we show to you, the clamping and the back calculation. In fact, we said that clamping can yield to poor transient response for large dead times. But the back calculation can be effective for plants with relatively large dead time. So in that sense, it's better to apply back calculation rather than clamping. Okay, clamping anti-windup. So let's see. This is basically the function 1 over 10s plus 1 e minus 2s. That's the controlled plan, the plan that we want to control. Alright, so we'll be looking at it. Yeah, so as we said, this is a transport delay, so you can have it by adding 2 seconds, because here you have a delay of 2 seconds. That's what they said to us. The plant has a 2-second delay. You can see it here. E minus 2s means a delay of 2 seconds. And the actuator saturate between minus 10 and 10. Alright, basically that's it. So they said if you want to launch it, just you can download it or simply type this in the command window, because it's a demo inherent for MATLAB user. So then if you write it, you will get the Simulink model. Okay, maybe it's a little bit slow, but it will open finally. Basically this is the result that you will see here. You see the output. Okay, so I have it now here. Alright, so here is your system. You have a reference input start at step time 80 is it went from 10 to 5. So basically what you have here is a step input that is at 10 and it moves to 5 at time equal 80 seconds. Okay, so that's your reference if you wish. Okay, that's your reference. It's called R of t. Then this is your R of t. This is your R of t. And here is the output Y. Actually, they put it as a scope, but you know, this is new type of scope. You can learn it yourself. It's not that hard, but how to create, basically you click on where you want to create and you right click and create and connect viewer Simulink scope, and that's how you create the scope. So you see now I have here scope. So then what else? Now if I run my system, okay, so I'm running it. If I click on it, it must give me the signal which is at the output of it. Alright, can I add other signal on it? So like 2 port for example? Yes, I can. Like you go to right click on it and go to scope manager, So this is scope number what? Let me scope number 2. It's called scope 2. So this is scope 2. You see it's first order process. Give it by default that name. You can then it also, if you are naming something on the wire itself, on the arrow itself, it takes the name of the arrow. But because not, so then it takes. So you can here add some other stuff, some other name you have, like signal here. Maybe I can add the input of and the output. So that's the input. Then this is going to be my signal. It has to, when you edit it here. So now if I click on it, maybe I need to run first again. Then this will be updated. Okay. So then I can see two things, just to tell you about. So then you can compare here or there. Yeah, that's it. So but I will close. I will delete it anyway because I don't want it. Delete viewer scope 2. Okay, so now it went out. So then what do I have in here in this scope? So you know how to make. Then what do I have? I'm creating two. I'm connecting two signal. Actually, the reference and the output, as we are doing usually. So here, your reference Y, your reference R, and the output Y. So as you can see, the R in blue from 10 at 80 seconds, it goes to 5. And here is, you can see the output. So where is the evidence of, let's say, where is the evidence of the 2-second delay? You can see it here. Like if you, for example, zoom in here a little bit at the beginning, you see that your signal start after 2 seconds. That's why you have the delay. After 2 seconds, your signal starts. So that's basically what it tells you, like you have a delay of 2 seconds. So here you have a delay of 2 seconds. But why you have more delay? Why you have more delay? Let's see what's going on here. What do we have? What I can see here in this. So here you can see the plant actuator. That's the actuator saturation between -10 and 10. And if I look at it, UT is just before the saturation, so which is the output of the controller, and satu like it's the saturated value, which is 10. So here it's saturating, so I can see my actuator is saturating actually, and then it goes, then they join each other. Alright, that's at least what I can see. So basically I will focus on these two signals. Okay, so I'll be focusing on this and this. Here I look to the output and the reference, and here I look to the, what do I have, output of the controller and after saturation, if it's saturated or not. So let's see what do I have in here. Alright, here that's tuned. As he said, he tuned it to you before having any anti-wind-up method applied, and that's how we didn't apply any anti-wind-up method. But he put a saturation block of the actuator, and without any anti-wind-up, but the actuator simulates the physical system, so the system is saturating. And then when I look to my output, well, my output doesn't react as it should be. So if you look to both signal, if you look to both signal, reference output and control signal, so what's going on here? Like yes, so in the yellow, in the blue curve, this how we understand the 2-second delay, because it's a delay, it has a delay time the process, but we don't understand why it is more than 2 seconds. So should at 82, alright, then it should react. So why it doesn't react? Here first, the system doesn't have overshoot, so they tune it in a way to don't give you overshoot. So here the system is not saturated, but there is a delay in here before going to the reference. So, and this delay also we call it wind up effect due to the saturation of your actuator. Each time your actuator saturates and you have an integrator, so it means you have wind up effect, and this is due to the wind up effect. How to reduce it? Maybe for you this is not critical, so you don't implement wind up effect in your physical system, because here saturation block means you are simulating the physical system. You can add friction, you can add, make it more and more reflect the reality. That's why when you have the real robot, the real physical system, sometimes you need to slightly also tune more to like to overcome everything in the physical system, which you didn't cover in the simulation. Anyway, so what's happening here? When I first commanded at 10, so we have error, but the controller give a signal which is very high to react from 0 to go to 10, and especially so have time delay. That's what make it after some time. So this time delay, as if you are holding your actuator, as you are holding your drone, same thing. So this time delay, I hold my drone for 2 seconds, for example. So after this time, my system will react. So I release my hand soon. So then, or in many chemical process, usually they have time delay. In many industrial process, they have time delay inherent in the system. You don't need to have your hand on the drone. So then, my system should react quickly to reach the set point, which is 10. For that, the controller give a high value, needs a high value. Why? Because in this 2 seconds also you have accumulated energy from the integrator, and you are far away from this. So this 2 seconds you are counting the error. So that's why it's saturated directly. So it requires 15, even more than 15. So at 2 seconds, below 2 seconds, it requires 15 or something like. So then maybe if I zoom, if I'm able to zoom, I can find, so yeah, around the before the 2 seconds, in this 2 seconds, so it requires actually started at 15. So from the beginning you need 15 to reach the 10, and this is normal at the beginning to have saturation for short time, because you started from high value reference. Okay, so what's going on in here? When I reach my set point around maybe less than 60, I reach my set point, then I should, here my error should be 0. So if I look to the error, it's a good idea to visualize the error, guys. Let's visualize the error in a new scope. Let's do as they are doing. Create simulating scope for the error. Okay, this is the error. Also, it's good to see it. In addition to here and there. Alright, quickly, here is my thing, and here is my error. Very nice. So at the beginning the error is 10 for this 2 seconds, the first 2 seconds, and I need more control. Then starting to decrease the error, because I'm moving toward 10, maybe toward less than 60, my error becomes 0. My error E of t is 0 now. So here, less than 60, my error becomes 0. So then your actuator should start going back. You should start going back. So what's happening here you are following the reference, your controller is able to tune it well at 10 to the saturation point, but your so here your control signal before saturation, it's saturated at during this time up to 80 at the 25, so it's 25 not 10, but actually the 10 is saturated, is enough. The 10 was enough to have no error. So that's how you tune your PID. You can tune it, you know how to tune your PID to have no overshoot. So you are the designer, you can do that. I can change the design if I wish to have overshoot, for example. So let me copy, Control C, Control V. Okay, when I copy it, I believe I copy it with all the value 1717. So let's tune it differently to have overshoot if you wish. Alright. That's a block response, a current response after the 2 seconds, and here everything is normalized, of course, and here is the tuned block, the blue one, not the dashed one. Maybe I do it this way. If I think that's what I want, then I update my block. So P4026, so it's updated. Then I say okay. I look to my signal now. So this is my signal, how it looks like. It looks like it's not overshooted. Alright. You see here the control effort at the beginning, so I have a lot of control effort to have a signal this way. Well, this signal looks like more faster, but no overshoot as well. Why doesn't overshoot? So let me, yeah, why doesn't overshoot? Most probably because of the saturation block you make. That's right. I'm giving, so basically it gives me same output here somehow, except in here when my actuator is not anymore saturated, because you know here is 40 even, not 25 as it was before. So high control signal from the actuator before saturated. But what the plant is seeing the 10. So it's seeing it as it's open loop, remember? So then if you are in this scenario, so then if you want to have overshoot as we saw in the tuned block, better to take out the plant actuator. You can take it out. So then the plant or the limit, put it maybe minus 40. Assuming now it's a simulation, so I'm saturating in here. So I'm changing the dynamic of my system. So you can see now some overshoot, and you can see here also still saturating at the beginning. So you have the saturation at 40 now. See, all right. That's this control signal, how it look like, and this is the signal. So it overshoot. Then we do the comparison. But now in our situation, okay, it is minus 1010. So this is prevent the saturation, and I will return the tuned one, which they did. So now okay, because we take it out, so then we need to add on it. So this is luckily still the same, but here we need to add on it the UT. It's alright how to add the UT. Right click, signal scope. It is called scope 1. It's called scope 1. Scope 1. It has SAT, but it should have UT as well. Okay, so now it has 2. So I rerun. I take it and I take this one. Alright, am I still seeing the error? This is my new error there. Let's have all together. Which signal I don't have? This. So now I have all. Good. Very nice. So then this is delay. The origin of what? So now when you reach the 50, the less than 60 here, your controller, the 10 that you are applying as the saturated one, is able to hold 0 error. Okay, then we are fine. Then what happens here at this point? I changed. Okay, I changed. We have 2-second delay. But what happens after this 2 seconds? When I change down, so my control signal will go down, right? So your control signal start to go down quickly because the system control is very nice. But the thing is, here is the point: the saturated output, the output still saturated because it's here go down to 20 or but still above 10, so it's saturated. So it's keep going saturated until you really reach the 10 and you go beyond the 10. So when you go beyond the 10 at this point, which is maybe somehow near 90, a little bit less here, when you reach here, this point, actually if you continue here, it is this point, same point as here. So when your output of the controller and output of the saturation block becomes the same, so at this point your plant is receiving a less control effort, so then it will start reduce to go to the reference, and therefore this extra timing here, in addition to the 2 seconds, without the 2 seconds, are due to the wind up effect, right? So now we understand what's going on here. Let's do same, but now having, okay, so now you have you can take this out because minus 10, 10, so you can take it out because it is inherently here. And so if I say none without, so it doesn't matter, clamping. Alright, and see the effect of clamping. Well, the clamp here is not going to be as good as the wind up back calculation method. Why? Because I have delay, and if the delay is more, then it will be, for large delay, it's worst, as we know. And let's look to my signal. I cannot see the saturation. Let's see why. Okay. Remember I added it, right? But let's add it again. Scope 1. It is here. UT and SAT. Okay. They are both here probably, but there is no saturation. Let's see everything, and that's the error. We'll try to check it together. And here is the signal. So that's my error. Here the delay time 2 seconds, and after this delay it will react. So here we have saturation, and it looks like your saturated output is same as your UT. So here there is no saturation, it's between 10 and minus 10. Means like you don't need, that's the effort you need actually, 10. I believe scope 1, let me delete UT, let me delete yes UT, and I deleted the whole scope. Alright, let's create it again. Okay, it's called scope 1. Surprise. No problem. It's called scope 1. Okay, then I add to it UT. I close. View legend. It seems they are the same. Then alright. It seems they are the same. Well, you can have same dimension scope if you wish. Just make sure no, you can compare them better this way. Like same scale. And you have the error. That's your error is here. So here it's better, there is no delay, and here the overshoot related to your controller performance. It overshoot, but you're still within the limit. So here both SAT and UT are following same trend. Okay, what if I do anti-clamping now? Back calculation method. If I go and do back calculation method, here let's keep it the default value, but you know you can have TR, which is square root TI TD, and you can compute the back calculation. You can compute the back calculation coefficient. But let's keep it as it is and check performance in here and there. And also one way you could compare, you know, here when you say SAT and UT, that's what confused me. They give you the same value simply because UT is already bounded as well. So that's making crazy. So it's already bounded. So it's bounded here. So then if there is a way with no need to bound it, like in the sense you keep it here unbounded, the default value of maybe it's infinity, right? If you have a saturation block, I guess we can have it infinity probably plus minus m. if I'm not wrong, just like you have nothing on. No, this is the one that I want to block. I want to make it infinity and minus infinity. At least I know, like, if I write PID in here and I take so inf minus inf. Okay, so this is the one I'm taking inf minus inf, so I'm not blocking it. And let's go to the clamping then. Alright, and here it's still minus 10 10. Okay, so in this way they should not be the same. Okay. Alright, so here it makes more sense, but okay, let's check what's going on here. That seems the same. Is it I do clamping here? Or is there a way to get the output of the controller? Let's see the result here. Without using anti-wind up, we saw it. With wind up, he was doing back calculation or clamping, right? He didn't. Yeah, he had same thing, UT and sat U, because yeah, he did it this way. So they are the same actually, because it's clamped here. And actually, if you don't clamp, it looks like if you don't clamp here, the inherent function inside MATLAB doesn't know that we need to have anti-wind up, because compared with infinity. So then this is something we need to do. No way. So then, and we cannot access, unfortunately, the output in this case. Then, alright, no problem, just we stick on this value. It makes more sense. And let's see the remaining one, which is in this case the back calculation, and we keep it 1 for instance. We can do the calculation, have better result as we did. And this is the output of. What's the difference between here in this photo? They show us the difference without anti-wind up and with anti-wind up. Basically here they don't do clamping, they did only back calculation, and they get this result same as the result we had. Actually it is. Here they did the comparison between both anti-wind up and wind up, and you see the difference in between. Without anti-wind up you have this delay, but with anti-wind up you don't have this delay, but you have slight overshoot, which is acceptable maybe for you, but you don't want to delay the process. And what if it is already delayed 2 seconds? Maybe it's more than 2 seconds, depends in your process. So then this is also one of the effects of on the wind up. That's an example. Okay, you can work on. They did clamping here. Alright, and that's it. That's everything. How to save the image and plot it in different place. So here you have the output. So you can go to your here and you have the output Y, and you have T if you wish T out somewhere, because probably T, it's by default it's get like as a timing, which is from 0 to, in this case, 200, right? 200 in our simulation runtime setting. Anyway, you can directly, if you want, just by default, if you type Y out, so you can print the Y out, okay, for you until okay, it print this way because it counts. And then if you wish to have exact thing, do T out, then Y out. Okay, so you get your system. You then hold on, and you do, when you do the other run, without clamping, you hold on another plot, so it will plot two on the same graph, so you can compare. That's it. So if we continue the exercise, so talking about anti-windup for saturated actuator with cascade dynamics. Okay, so here the question is, what if I have some dynamics, some input dynamics of my actuator and an output dynamic of my actuator? So how do I deal with the wind-up effect in this scenario? If I'm in this case like this, well, basically nothing new. What you do is as what we are doing here. Okay, you take the output from here and the input from here, you subtract them, and you multiply by your coefficient, proportional coefficient, anti-wind-up constant, which is 1 over TR, and then etc. Right? Exactly the same. And that's what we did in previous scenario inherently when we make our PID, then we put the saturation limit inside and so on. But here you see there is no saturation limit. They didn't mention any saturation limit. So then, however, what they did, so you don't mention saturation limit, but you mention something else, like that's your PID controller. So instead of showing the limit and later on the method that you want to do, what you do is you go to initialization and enable tracking mode, and here KT is exactly same as your KB. You need to tune it. How to tune this value is you find the TR, and this is 1 over TR. So as we did in as we know actually how to make. Alright, so nothing different, just you enter it here, and inherently if you follow the mask inside the PID how it's built, you will find, so how to follow the mask look under the mask and you look to the PID. If you follow it, I don't recommend you to do because time consuming, but anyway, when you do, you will find out it's exactly MATLAB is building exact same function as there. But the thing, so why we didn't use the previous method? Simply we didn't use the previous method because what you care about is here and there. These are the 2 points that we care about. Okay, so when you provide this signal to MATLAB and MATLAB knows this signal, then they subtract them together and they multiply them by the coefficient K that you give it to it, KT. It's called KT, right? In here, it's called KT. So they multiply it by the coefficient. The thing, because previously, in the previous exercise, you put the limit -10 to 10 and you assume that's your dynamic, so then you know, so MATLAB directly know in here it's -10 and here is 10, and then they take them together, they find the error and they multiply. So you don't, but here in this case, this is not that we are interested on. We are not interested in these 2 points. However, we are interested in to subtract this point from this point. So the saturated error for me is here minus here. Okay, those are the saturated error for me, because I have dynamics at the input and dynamics at the output of the actuator. If in a real scenario I have this kind of things, like I have dynamics here and dynamics here, then this is how your system, so then you need to feed back the saturated output or the output of the actuator dynamic. So because it's more likely your actuator is not gonna be like this, -10 to 10. You should have dynamic at the input and dynamic at the output. Anyway, let's run it and look what's giving to you. Okay, this is with the wind up effect, not without. It's with the wind up effect, with the anti-wind up effect. Means this is a good way. Otherwise, if you don't have the anti-wind up effect, you can look to the performance of your system if you wish. Okay, so for example, and then you can compare. If I don't have this one, I can do my simulation and look. That's how it looks like. Alright, so you can compare them if you wish. But when you put it, even it's taking it as one. Sometimes one is enough, but better for more precisely to have better even things to compute it as we learned in class in general. But one is most of the time is enough. Alright, so now if I look to my output, that's how it looks. It looks better. Okay. Let's look to here. It's UT and the UT sat. That's UT sat. So comparing this, the output of your controller, to the UT saturation, which is here. Okay, that's your saturation. That's the dynamic. Actually, it's not, as you could imagine, it's minus 10 to 10. It's not like minus 10 to 10. The actuator has different dynamics, which is, let me keep it more minimal. Alright, maybe it's not clear to see it here. So that's the saturation one. Okay, this is better. If I look here, so see here it's 10. Alright, so if I look here, this is UT at the beginning, and this is the saturated output. So it has dynamics. It's not like, so it doesn't give you saturation like this saturated one. If it is minus 10 to 10, if it is high, the controller, so it will be 10. Maybe it has some dynamics, and that's mostly what happens. So you are applying at the input some dynamics, and it will give you here things. So this is reflect more the realistic actuator. That's the model of your actuator, in out. Alright. Most often those two, you can consider them as the same, before and after, or slight difference. So it depends, and usually it's the same model. In general, it's the same actuator. Okay, so you can take same signal if you wish. At least that's my understanding. So you can have them the same. And you know, like for example, your actuator saturate minus 10 to 10, but with some dynamic. Not that big difference. Yeah. So hopefully you understand it. Also, if you wish, you can go here. Okay, for Paul Aquatella, and you look to the Astrom textbook. You will find some information. By the way, this textbook, Okay, this chapter from the textbook. I'm not sure if the whole textbook is there. At least you find a lot of courses here. I'm not sure it's forbidden at least, but the link is, you have access to it. Alright. That's it about. If you go to the reference, you find a lot of interesting information. Maybe if you go, may it get confused you, so I recommend you to really follow our lecture because everything in is we already know. Remaining one is they said, what if I have PID with feed forward? Now I have some feed forward in the system, so what should I do in the case of anti-windup effect? Let's see. So quickly, what's this exercise is about, or this tutorial is about? Okay, it's a laughing exercise, laughing tutorial actually. You know, uh, again and again, we know what's the it's all doing the back calculation, as we saw in our slides, in our slides here. So u minus v. All right, so we are looking always to figure out what's u and what's v. And now KAW, we are taking it as one as well in this exercise, that you know how to compute better value if you wish. But one, most often, it's enough. Compared it with without, it's most often is enough. So let me say, yeah. So what's happening here? Assume in your control you want to add, for some reason which we don't want to talk about it now, at least you want to add a gain directly that go from your reference, from your set point, add it to your actuator that goes to the plant, add it to your output control signal. So this is the output control signal. So you add on it a signal, so that's its sum of here, it goes to the actuator. So assuming in addition to the output of your PID controller, you need to add on it a feed forward controller, that we call it feed forward controller. For a reason, you want to add it directly goes from your reference and added it here. So then your goal is anti-windup. So anti-windup, basically we said this minus this. But what is it? So this minus this inherently doing on MATLAB. But what is the signal here? The signal here is basically, that's the signal we care about. Alright, so if that's the signal we care about, then you need usually the signal is this signal minus this signal, and this signal, it is actually this one, the output of your controller. Remember, again that's your PID, that's the output of the controller, so we care about the signal. And here, so this signal is MATLAB knowing it. MATLAB knows this signal, so the point here, MATLAB knows it. Still, the point here, so I need to take it, I feed it back as we did in the previous tutorial. I feed it back, I need to feed it this to here. So then MATLAB will take this minus this, multiply them by the coefficients that you put, and doing here. This is subtract them, multiply by this, and integrate it here. All of those are inside the mask. But if you look, what you are doing here is not exactly the same. So basically, that signal that you need to subtract from it whatever you added on, because this effect is an additional effect we don't care about. Basically, we care about the signal that came out directly from the actuator as if this doesn't exist. But this is we need to put, for some reason in my controller I need to add a feed forward controller. So if this is something I need to have, I cannot cut it out. If I can cut it out, then we are fine. But I cannot cut it out. Then I subtract it from your output here. Remember, that's what you want to feed back. So I subtract its effect as if it doesn't exist, and I feed it. Okay, and that's what he's doing. That's why I'm saying it's a laughing exercise. Okay, but yeah, in case otherwise, if you don't want to go into this complicated stuff, you can. If you don't want to go into this and even the below one, you can, and you stick on applying directly what we said here. So then you need to build your own PID, and it's easy then to build your own PID. You put the proportional, the integral, derivative, but pay attention about the derivative. The derivative, you need to add the filter on it, or sometimes you need to have it in, instead of having error, you could feed directly the output, integrate, derive the output. All right, so then you could do it yourself, build the system yourself, and make your life easy. This is also possible. But if you don't want, then here in this tutorial, MATLAB is teaching us how to counteract everything you added into your system. All right, so if you ask me what's my preferences is to go this way, because this way I have the fact that I can tune myself. I can do auto tuning for my parameters, so that's why I prefer to go this way. Last remark, feed forward is important sometimes to improve the transient response of your system. So, and usually because the controller sometimes it takes, especially if there is a delay, it becomes important, because the controller needs some time to react to your reference. But one way to turn around this issue is to add feed forward control and directly feed your signal to the actuator. And basically here what we do, we put a gain, and this gain, which is here, it's not 1 in general, it is 1 over the DC gain of your plant. So because imagine, so that is that's my DC gain of my plant, assuming it's equal to A, okay, or K if you wish. And then that's the DC gain of my plant. And then if at the beginning, before this transient happened and so on, if I multiply by 1 over K, so roughly speaking, like your reference and this is your output, it's gonna be, so then you improve your response, because your reference direct, your output will follow quickly your response. And this is important if the transient response is slow and if you have delay, as we saw in the previous dynamic. When I add dynamic here and here, then my system becomes a little bit slow. Then so why then they put 1? They could put 1 over the DC gain. What is the DC gain of this transfer function? A over TS plus 1. So the T is 10 and A is 1. Okay, so that's why 1 over 1 give you 1. Okay, that's it for this tutorial, Simulink. I recommend you to watch yourself, practice it, is alright. This is basically simulation.